In this lesson, we'll be learning about some of the few nuclear processes you need to know about in high school chemistry. Nuclear processes like decay, fission, and fusion. The decay processes you need to know about in high school chemistry include alpha radiation, beta radiation, and gamma radiation. And then we also need to know about a sort of a separate category of fission and fusion processes. Okay, so let's just do a real quick review of the things we've already more or less covered. You have a copy of test references, and I'm going to pull out not the first periodic table. If you're in an honors class, then let me just tell you this on the references, okay? On the test, you won't have this whole packet. On the test, you're going to have this page and the periodic table that's on the back page. You're going to have this set of references, and that's it. Okay, all this other stuff is for you to refer to as needed for homework and that sort of thing. Okay, it's to help you get ready for it, but you'll have to know things that are in this larger set of materials that you won't see on here. So there's some memorization going to be involved in getting ready for the test. One of the things you may notice right now, since we're talking about the periodic table, is that this periodic table that you're going to be using, oh, there's an error there. No, that's good. Is there's no names on this. Okay, so you've got to know the names of those elements that we're going to be using, mostly you know, down through the third row or so. Okay, down through here, probably sometimes over here, but just the one. Well, actually, fourth row if you include hydrogen. But a more complete periodic table is found right here, and this has the average atomic mass is worked out to a greater precision. Okay, so this is the atomic number that represents the number of protons. Elements are identified by their protons. So all nickels have 28 protons, but not all nickels have the same number of neutrons, and that is where we get isotopes from. Isotopes are different forms of the same element, differing only in the atomic mass, because they're also differing in the number of neutrons. And so this average atomic mass is the weighted average of all the different known isotopes for nickel. Okay, so isotopes might have there might be two forms of nickel, but they have, and the two different forms, or three forms, or four forms, whatever it happens to be, would be differing in the number of neutrons, not in the number of protons. Protons are the same. Now, as long as you have an atom, atoms are neutrally charged. Protons are positively charged. This should be a review from your physical science class and probably other classes. Protons are positively charged. Atoms are neutral, so there has to be an opposite charge included in there, and that's where the electrons come from. And so all the electrons are negatively charged, and you have an equal number of protons and electrons in an atom. One of the things you're going to find out about in this class is that there are things called ions, where you don't have an equal number of protons and electrons. And so in that case, then, you can't just depend that all the electrons are going to be 28 for all nickels. That's not the way it works. Okay? Nickels tend to adopt a 2+ charge when they're combining with other things, and in that case, they're losing 2 electrons, and so they have 2 more protons than electrons. That's where the positive charge comes from. Okay? Now, that's a subject for a future class, but I'm just kind of giving you a heads up. That's where we're going. Okay? So this doesn't tell you what the actual atomic mass of all nickels are. None of these atomic masses tell you that. Okay, we have to look in this unit at the isotope, the actual atomic mass of a particular isotope of nickel, and that's what we're going to be talking about a little bit today. Now, one of the things we talked about leading up to this class is about nuclear decay, nuclear fusion, and nuclear fission, and we said that decay is when elements break down in little bits. Okay, little pieces. There's alpha decay, which an alpha particle means you're losing 2 protons, 2 neutrons from the nucleus. For all practical purposes, an alpha particle has the same structure as the nucleus of a helium atom. It's not a helium atom because a helium atom also has electrons, and what's coming out of the nucleus has no electrons. So an alpha particle has a 2+ charge because it has 2 protons but no electrons to balance out that charge. Okay, then you got beta decay. Beta particles are, for all practical purposes, they have the same structure as an electron. Electrons have a negative charge, have very, very small mass, and so we consider it so small, we basically say it's zero mass. okay, because it's almost 2,000 times smaller in mass than a proton and a neutron. And when we talk about the mass here of these atoms, we're talking about the sum of protons and neutrons. A proton has an atomic mass unit of 1. A neutron has an atomic mass unit of 1. And this average atomic mass here is weighed in atomic mass units, which has a symbol of a small letter U. Okay? So then you got those beta particles. They are electrons essentially that are coming out of a neutron. Electrons are negative. So when that negative charge comes out of a neutron, which is neutral, what you have left is something with a positive charge with virtually the same mass. So essentially you're creating a proton. So we have beta decay. Every beta particle that comes out creates an extra proton. That makes sense? So when you have alpha decay, you're changing the element to something that has an atomic number 2 places smaller. So uranium goes through alpha decay, and what you have left when a uranium atom goes through alpha decay is thorium, because it has 2 protons less. Okay, when you go through beta decay, on the other hand, carbon here, carbon 14, goes through beta decay, and when that happens, you create an extra proton. So when you have beta decay for carbon 14, you create nitrogen because you're actually adding an extra proton there. Okay, and then you have gamma radiation. Those are the only 3 forms of radiation you need to know about in here: alpha, beta, gamma, A, B, C in the Greek alphabet. Gamma radiation doesn't change anything in the nucleus. I mean, it does, but not enough to matter to us. It changes the mass a little bit, but it's so small we just ignore it. So gamma radiation emits gamma electromagnetic radiation. It's like light, only with a really much smaller wavelength than the light we can see. So what you're seeing here on this screen is a tiny, thin little slice of the electromagnetic spectrum that we can see. Okay, human beings can't see much of the electromagnetic spectrum at all. Just a tiny little piece, somewhere near the middle, slightly, well, maybe if you look at the whole spectrum, we're maybe a third from the bottom, so to speak. Radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays, they're all part of the electromagnetic spectrum. They're all the same stuff, just different wavelengths, okay? So that's kind of the quick overview and bringing you up to speed to where we are right now. You got all that? Okay, I can give you a quiz on it right now. Y'all all aced it, right? Mm-hmm. Okay, anyway. What I want to talk about now is how we're going to do nuclear equations. And I gave you all a handout with some little equations on it, right? We're going to use that later. Right now I'm going to start with just showing you how this works, okay? All right, so we need to know how to write symbols here for isotopes and for these particles we just talked about, okay? So I mentioned uranium. Uranium has 2 different isotopes. You've got uranium-235. Oh, my screen just went blank here. You've got uranium-235, and so when you're going to write the nuclear symbol for uranium, and of course my marker is not going to write very well. All right, so U is the symbol for uranium, okay? And we're going to write a nuclear symbol for it. When we're talking about nuclear equations, we need to look at which isotope we're dealing with, okay? So let's start with uranium-238. That's the most common isotope of uranium, 238. There's the mass, and that's why we call it uranium-238. If we were giving this a name, we would call this uranium-238, which we can also write as U-238 or uranium-238. Okay. Now, notice that the element symbol always starts with a capital letter. If we look at the element symbols on here, if there's a single letter for the element symbol, it's a capital letter. If there's two letters in the element symbol, then you're going to have a capital letter followed by a small letter. Now, when you're writing these, please make sure that you write them that way. Okay. Do not write arsenic as a capital A and an S the same size, because I don't know what you mean by that. If you don't write it as a capital S and a clearly half-size S, next compared to the A anyway, I don't know that it's arsenic, okay? So be clear about what you mean. If you're not used to doing that, get used to it. It's not the correct symbol unless you have a clearly capital letter and if necessary followed by a small letter. Or if you have one of these new elements I haven't put on this periodic table, I need to put it on here. I'm not sure why it's not printed out here. But then you're going to have 3 letters for it because they're kind of placekeepers until the International Union of Pure and Applied Chemistry decides on what those names are going to be. And by the way, that is the organization that makes all the decisions about how we name things in chemistry. International Union of Pure and Applied Chemistry. Okay, there's also a Pure and Applied Physics group as well. All right, so we capitalize this letter, but when we write the names of elements are not proper nouns. I hope you remember from English what a proper noun is. It means you have to capitalize it. So if I write your name, I'm supposed to capitalize the first letter of your name. If I write a name of a city, I'm supposed to capitalize the first letter in the city or the state or a country. These are not proper nouns. So the only time you're going to capitalize the name of an element is when it appears as the first word in a sentence or if it's part of a title or something. Okay? So this is not a proper noun. Please don't capitalize them. Don't make a habit of capitalizing them. All right. So this is the mass of this particular isotope of uranium. Now that's really enough. Okay? And in some later classes, you may be asked to write your symbols for isotopes in just this way and nothing else. Okay? Or maybe just this way and nothing else. But for the math that we're going to do to balance these equations, I want you to write the atomic number down here. Okay? Uranium's atomic number is always 92. All uraniums are always 92 because that's how you identify elements. Okay? All right. Now, we said that uranium a minute ago goes through something called alpha decay. All right? So what we're going to do is we're going to take this uranium, we're going to show it going through alpha decay. So the result is when it goes through this alpha decay, we're going to have an alpha particle over here. Now, if you remember, we said an alpha particle looks something like this. Okay? I've heard students say that was like a Jesus fish. Okay? But it's more or less like a small letter A with a little sort of swish on the top here. And we said an alpha particle has 2 protons and 2 neutrons. Protons have an atomic mass of, come on, fill in the blank for me. Protons have an atomic mass of 1. Good. Neutrons have an atomic mass of 1. Really easy here. 1, okay? Both of them are 1, all right? So if I have 2 protons and 2 neutrons, what's the mass of an alpha particle? 4. Good. So that's an atomic mass of 4. What's its atomic number? 2 protons. So we're going to put the 2 down here at the bottom. Okay? Now then, if this alpha particle is leaving this uranium, we got to have something else over here for this to be balanced. When we're balancing equations, we treat this arrow as if it's an equal sign. It's not a true equal sign because what it's saying is we're going from this to this. But if we're going to not violate the law of conservation of mass, and the law of conservation of mass is only true in chemical equations, and we're in chemistry, so we can do this. So if we're not going to violate the law of conservation of mass, I need to have the same mass on this side as on this side. Okay? So what is the rest of the mass that I need over here?
234.
234. So I need something else that has a mass of 234. Okay? And what's the atomic number I'm going to need? Because I can't destroy protons. I've got 92 protons here and 2 protons here. I got to have some more protons on the right to have everything balance out. How many protons do I need? 90. You can speak up. It's okay. You're not going to be in trouble because you say the wrong answer. It's all right, because in this class, everybody has to be wrong some, right? If you're going to be doing science, you're going to be wrong some. All right? Don't be afraid. And so what element has an atomic number of 90? Thorium. Yep, there it is. Atomic number of 90. There's thorium. So this is thorium. Okay? When uranium goes through alpha decay, you have an alpha particle and you have thorium. That makes sense? That's all there is to balancing nuclear equations. Now we got to know these other particles, okay? So the other particles we need to know about include beta particles. Remember, beta symbols look like this, okay? And we assume their mass to be 0 because the mass is really so small that it doesn't matter. Beta particles are essentially electrons. Electrons have 1/2000th of the mass of a proton or neutron. So rather than write 0.00, you know, that sort of stuff. We're just going to write 0 because it's essentially 0. It doesn't really matter much to what we're doing, okay? And because when we emit a beta particle from a neutron, we increase the number of protons by 1 because when you pull the beta particle out of a neutron, it's negatively charged. It leaves behind a particle that has a mass of 1 and a charge of a positive. And that's what a proton is, okay? So to make that math work out, we're going to say this is a -1 atomic number. Now, just for the record, there is no such thing as a -1 atomic number, okay? Atomic numbers are the number of protons, and you can't have a negative proton, all right? That's like saying, you know, I don't know what that means. So it's not real, okay? And we're dealing in the world of reality with chemistry, okay? But this is just making the math easier, okay? That's one of the symbols you need to know. Another one you need to know is what gamma radiation looks like. And gamma radiation, the symbol for gamma, is like a script L that you spun around 180 degrees. So let's spin this back around this way a minute. Notice that it looks like a script L, right? And so I'll do it this way, and I got a gamma symbol, okay? Not flipped upside down, but spun, okay? All right, and so its atomic mass is for electromagnetic radiation comes in these little packets of waves called photons. Okay, well, photons have even less mass than electrons. Okay, almost no mass at all. I mean, if electrons are 0, well, photons are going to be 0. So the photons are going to be 0. We're not changing the protons, so that's an atomic number of 0. So there's your symbol for purposes of doing nuclear equations. That's your symbol for gamma radiation. And one more you need to know, because these are involved in fission and fusion in particular, and that's how you're going to write the symbol, a nuclear symbol for a neutron. So lowercase n. And what's the mass of a neutron? Don't everybody speak at once. 1, yes. Remember, neutrons and protons both have an atomic mass of 1. So where does that number go? Upper left. Okay, always upper left, not upper right. Upper right is for something else. All the 4 corners here have a different, it means something different. Yeah.
So can any element go through any of those decays, or can uranium only go through alpha decay?
Well, uranium, actually, I suppose that's a really big question. Can. While I suppose it's possible, it almost never happens. So uranium always, almost always, virtually always happens that it goes through alpha decay. Okay? And so there's no protons here. It's just a neutron. What's the atomic number here for a neutron? 0. There you go. There's your nuclear symbol for neutrons, okay? Now, just a kind of a heads up, tomorrow we're going to do a lab, but there's no pre-lab to do, okay? You just got to come dressed properly for labs tomorrow, okay? And you're going to get a chance to see evidence that alpha particles really do exist. And we're really going to be working with uranium, okay? Uranium is, it's radioactive, okay? But this is low-grade uranium ore. It means it's a rock we dig out of the ground that has very little uranium in it. And almost all the uranium is 238, which isn't nearly as reactive as 235, which is what we need to use a lot of to make nuclear power and nuclear bombs and things like that. You'll get more radiation in a day from the concrete walls in this building than you will from our lab tomorrow. Okay, just saying. We're going to have a little bitty rock of uranium, and we're just going to be watching it. Watch what happens when we do something with it, okay, and see evidence of alpha particles, all right? Not actual alpha particles. You can't see alpha particles. Too small. Move too fast. Can't see them. But we're going to see evidence of them, all right? Got it? All right, so just remember to come dressed properly for a lab tomorrow. Put that on your reminder. Put it on your calendar. I use my phone. I just tell my phone, okay, remind me tomorrow. You know, y'all do that? Yeah, that's what I do, because that's how I keep up with stuff. Huh? I know, it's hard to remember if you don't do all that stuff. Okay, so that's this. We're going to be completing these kinds of equations with this information. Okay, all right. So let's try one. Let me just throw one at you here, and you guys try to see if you can fill in the blanks with some of this stuff. All right. So it turns out that thorium also goes through some kind of decay, and I'm going to give you a partial equation, and I want you to finish it out. Okay, so I said we're going to use thorium, so let's go ahead and put TH down here for thorium. Okay, so using this incomplete nuclear equation and the examples of the symbols for alpha, beta, gamma, and the neutron that I gave you earlier. See if you can figure out how to finish this equation. Remember, what's on the left of the arrow needs to equal what's on the right of the arrow. So the masses across the top need to be the same on both sides, and the atomic number across the bottom needs to be the same. All right, so if you're watching this video at home, you should at least get the work done before you come back and solve the problem. So let's see what goes in here. Thorium's atomic number is, don't everybody speak at once. What particle do you think is going to fit here? Alpha. All right, now helium. It could be helium. You're right. But here's the thing. You've got to look at it in context. So if we're doing fusion, where we're combining two things together, two elements together to get a larger piece of element or something, then I probably would call that helium. In fact, that's what you're required to do. Okay? But if I'm clearly going through some kind of decay, then it has to be an alpha particle. All right? So if I have 232 here, and as a result of this thing going on, we got 4 of these, then what does this number need to be? 228. Okay, and this number down here needs to be what? 88. And what element is that? Radium. And there's the symbol for radium. You just look it up on the periodic table. That makes sense? Everybody good with that? Okay. Let's see here. How about we do this one? Just, I don't know if I want. Should I just let you all do work on the handout? Why don't we do that? I think y'all pretty much understand, don't you? Y'all can collaborate a little bit. But here's the handout. So I'm gonna let y'all do a few of these in class, and then you can finish the rest of it at home. I'll give you a little bit of time to get started on it. Okay? So now let's talk a little bit about fission and fusion. And we talked a little bit about this already. I want to be clear about how you tell the difference between decay and then say fission and fusion. All right. So decay means we got little particles coming out. Okay. Decay means we have little particles coming out. All right. So these are all little alpha, beta, gamma, neutrons. If neutrons are being emitted, then that's decay. Now neutrons are more often than not actually not involved so much in decay as they are involved in fusion or fission. Now we do get some neutrons coming out when we do fusion, for example, and we'll see that. But mostly what you're looking for is the type of particle, the way that it's happening. All right. So when we have decay, by the way, that's called radiation as well. When we have lots of alpha particles coming out, that's alpha radiation. Okay, so alpha decay results in alpha radiation. Alpha decay results in alpha radiation. So decay is what happens when it's coming out of the nucleus. The radiation is the result of a lot of those coming out. Okay? Beta is the same way. We got beta radiation that comes from beta decay. So the result of a nucleus decaying through this process of beta emission is called, you get all these beta particles coming out, we call that beta radiation. Okay? So you've got 3 words here. Decay, that's the process of the nucleus breaking down. You've got emission, which is the process of those particles, or electromagnetic radiation in the case of gamma radiation. Even that's particles really, because it's photons. That emission is giving it away, where it's leaving the nucleus or leaving the substance. And then you've got radiation, which is the combination of a lot of these together. That makes sense? So just 3 terms to know. Decay, emission, radiation. All right? Decay is when it actually breaks down. Emission is when the particles are given away. Radiation is the combination of all those particles being given away, and then what they're doing after they leave the nucleus or leave the substance, when they reach you, for example. All right, and then you've got a separate category of fusion and fission. Now that means that instead of these small particles like this, okay, what we're going to get are large chunks, okay, large pieces as a result. let's look at this one, for example. Let's use uranium again. Well, this time we're going to use 235 because it's much more radioactive. It's much less stable, okay? When I say an element is radioactive, I mean by that it is not stable. The nuclei in that substance tends to break down, and you get radiation, you get emission, you get decay, okay? Unstable, all right? So the universe is tending towards stability, and the reason that these isotopes are radioactive is because they're not stable. And the result is they're trying to break up into pieces that are more stable than what you started with. That makes sense? Okay. So here's uranium-235. And in order to initiate fission, you have to have a trigger. Okay. Fission doesn't occur usually just on its own. I mean, it can, but it doesn't usually just happen on its own. All right. In order for it to happen, you have to kind of stick an extra something on there. And a lot of times we misunderstand that. People think of the thing you stick on there as kind of being like a bullet that breaks it apart. That's not really what happens. The nucleus of these large atoms like this are unstable. We often think about nuclei as being something that's, hard and stable. Okay? When we talk about J.J. Thomson discovering the nucleus, we say he fired alpha particles at gold foil and the alpha particles bounced off the hard nucleus. Well, compared to the electron cloud, it is harder. The electron cloud is almost all space. Okay, there's almost nothing except these widely spaced electrons in the electron cloud. If we were to, this is a pretty good sized school, okay, like 2,500 students, or actually it's getting closer to 3,000 now. If you were to put a tennis ball on the reception desk down front, okay, and that were the size of a small atom nucleus, for example, all right, the electron cloud, let's say we're talking about carbon. Carbon has an atomic, has a mass of 12. It has an atomic number of 6, so it has 6 protons. Most carbons have also 6 neutrons. So this little tiny tennis ball sized nucleus on the front desk, at the reception desk down front. And then so that means you also have these 6 electrons. And those 6 electrons are spaced out, relatively speaking, in a huge area. The edge of the electron cloud would extend all the way to the outside doors at A and B wing, not including C wing, okay? I mean, that might include C wing too, but pretty much A and that's a pretty big space with only 6 electrons in there. Now, they're moving really, really fast, and they're doing a lot of good stuff, but it's mostly space, okay? So, I don't know really why I was talking about that, except we're talking about the structure of the atom here. But if we're trying to break up this nucleus, we're trying to cause fission, we often think about the nucleus being hard and the electron cloud being soft, and it is in a sense, okay? Well, but it's not static. Hard doesn't mean it's static in that respect, okay? So if you think of the nucleus as, of a large atom anyway, I want you to stop thinking about it being something that's hard, but that it's like Jell-O, If you had a really slow motion camera and you saw Jell-O being a chunk of Jell-O being thrown across the room, it would be wiggling around, right? Right? Well, that's why I want you to think of the nucleus of these large atoms. They're wiggling around, all right? Well, when you add something else to that nucleus that makes it even more unstable than it was to start with, then it wants to break down, and it was unstable anyway. It wants to break apart. It wants to go through this decay process. But if you stick something else in there that makes it even more unstable, it'll do more than just go through this alpha decay. It'll break up into big chunks. Okay, so we're going to go from one big chunk to 2 smaller chunks. They won't be exactly the same size, but they're much bigger chunks. Okay, so we're going to add to this nucleus something that's going to make it break apart. And let me give you these numbers and you can figure out the rest of it, okay? We're going to let you fill in the rest of it. All right? Now, as a result of doing that, then, we're going to get some larger chunks of stuff. Chunks of stuff, okay? So let's see. Let's say we got an element over here that has a mass of 93. And let me give you the atomic number and you can figure out what the element is or what the isotope. Well, this is the isotope, but you're looking for the element. And then you're going to get another big chunk, Oh, I'm sorry, that should be a plus sign. Plus, I'm going to go ahead and tell you this is going to be barium. And this has an atomic mass of 140, but you got to figure out the atomic number. All right. And then as a result of this process, which you'll finish out for me here, we're going to have neutrons over here, and you're going to figure out the atomic mass and the atomic number. And I'm going to just give you a heads up that we got more than one neutron, so we got to put a coefficient out in front to tell me how many neutrons to do. Okay? So you can finish that up and we'll talk about it in a second, okay? All right then, let's see. Uranium has an atomic number of, just to make sure everybody understands, it's coming from this number here, 92. The only particle that has an atomic mass of 1, an atomic number of 0 is a neutron. We had it up here. Okay. Now then the atomic, this atomic number here tells us what this element's going to be, so we just look on the periodic table and see that we have krypton. Okay, just for the record, Krypton is also an imaginary planet from which Superman and Supergirl hail. Okay, there is no planet we know of that's actually Krypton, and by the way, there is no kryptonite. Doesn't exist. Just for the record. Okay, so you guys don't seem to be impressed by that, but anyway. So barium's atomic number is 56, and so if we add up all the masses on the left, we got a total mass on the left of 236, and a total atomic number on the left of 92. So we need all the numbers on the top over here to add up to 236. Let's see. All right, so what we have right now is we've got a mass of 93, and we've got a mass of 140, and so that's 233. So we need a mass 3 more than what we have so far. Does that make sense? And so this over here needs to be 3 more, but we've only got an atomic mass of 1 for a neutron, right? You can't make it 3, all right? You can't change what the universe, says it is. It isn't a mass of 1. So what we need is a coefficient of 3 here. Does that make sense? And this is 36 and 56, which adds up to 92, and that would give a 0 here, which makes sense because a neutron has an atomic number of 0. That makes sense? That work out okay? All right. So we have one big atom here, okay, uranium-235, and we'll put one little tiny neutron to it, okay? We add that on there. So that atom-235, the nucleus is big and wiggly, and it's squishing around like this, and we add that neutron to it, and that's enough to make it really unstable. And that instability is so great that it breaks up into smaller chunks. So we got krypton, and I just don't have room to put the 93 in there. I'm going to put it down in the bottom. And we got barium, a little bit bigger than krypton, but I didn't make it much bigger, 140. And we got 3 neutrons. Okay? And this is the basis behind the idea behind fission, but it's also where we get a chain reaction. Okay? So the chain reaction then, if we have this big particle here that you add a neutron to, as a result then we're going to get these 2 smaller particles of krypton and barium. And then as a result we also got more neutrons that go along and hit more uranium-235s. And those uranium-235s then, it doesn't hit them and just like explode them. It just sticks and makes it more unstable. They fall apart, okay? And those go along and give away 3 more neutrons. And pretty soon you got a huge number of uranium-235s that are breaking apart, okay? They're giving off all this energy at the same time, and we get a nuclear explosion. Or if we're controlling it, we get nuclear power from a nuclear power plant. That make sense? Yes? Okay. And it happens really, really fast. So that's why you have to control it inside a nuclear power plant. All right. It's a really interesting thing about how they go out doing all that controlling of it. All right. Now let's take a look. That's the way that fission works, splitting the atom. Okay. You cause something make this so unstable it doesn't just go through alpha decay, it goes through fission. Okay? Neat story about how that was discovered. This guy in Germany got the Nobel Prize for it, and some people think he didn't deserve it, that a woman deserved it, but back then women didn't get Nobel Prizes, so, you know. Anyway. She was also Jewish, so that's another thing that's going on against her. So, let's see. Let's talk about fusion then. So with fusion then, what we have are smaller elements that are being pushed together with a huge amount of pressure and heat to make something larger. Now, in the center of the sun, we theorize that there's a lot of things going on. We often say that it's just hydrogens being mushed together to make helium, but hydrogen's, normal hydrogen anyway, doesn't have any neutrons, and heliums have to have 2 neutrons, okay? So what's really happening is you get these different isotopes of hydrogen that we've already talked about. Normal hydrogen has no neutrons, that's just called normal hydrogen, or just hydrogen. Then you've got hydrogens that have a neutron, and that's called deuterium. Okay, we talked about that already? You know that. And then you got the type of hydrogen that Dr. Octopus wanted in the Spider-Man movies, and that's tritium. Okay? And so if you take, say, hydrogen that is actually deuterium, so this is hydrogen 2, and with a lot of heat and pressure we mash it together with a hydrogen that is really tritium, so it's got 2 neutrons, and put them together. Then as a result then, we'll get a temporary form of helium that's going to be very unstable. So this helium is going to have a mass of 5, helium-5. It's going to have 2 neutrons, 2 protons from the 2 hydrogens, but it's going to have 3 neutrons. It makes it very unstable. So this is a very, really, really temporary. This thing doesn't even stick around for, part of a second. It's going to blow apart, all right? And as a result then, we're going to get a normal helium, which is helium-4, and we're going to give away a neutron. That makes sense? Everybody understand what's happening? Okay, so what I'm going to let you do is take this illustration and let you write a nuclear equation for that. Okay? So write a nuclear equation the way that we've been writing nuclear equations, these things here, okay, that represents this process. Okay, so atomic mass of 2 for this hydrogen, an atomic number of 1 because all hydrogens have 1 proton, they have an atomic number of 1. We're putting it together with another hydrogen. This is tritium with a mass of 3, an atomic number 1. We put it together, we get helium that temporarily at least has a mass of 5 and atomic number of 2 because all heliums have 2 protons, and they're putting these 2 together. This side is equal to this, but this doesn't stay like that. That's temporary. And the result is we get this helium over here that has a mass of 4, an atomic number of 2, and we get a neutron which has a mass of 1, and atomic number of 0. Is that what you got? Or pretty close to it anyway? All right. A lot of times we just leave this out because, like I said, it's a temporary stage. It's not even there for tiny fractions of it. It's tiny, tiny, tiny fractions of a second, so it doesn't really matter. But this represents what's happening with fusion. Okay, it's one type of fusion. All right. So when you're working with this, and we get over here, we're not going to call this an alpha particle. Okay, we're going to call this helium because we're taking 2 hydrogens together and making it into something bigger. All right. So if it's breaking down something, that's alpha radiation. You'll give it an alpha symbol. All right. If it's building up something into helium, then you can call it helium. Does that make sense? Everybody good with that? That might be the only tricky part in any of this stuff, I think. Okay. Everybody good? And y'all can finish the worksheet at home, right? Yes? Mm-hmm. All right, good. Between these types of, let's talk about the comparisons between these types of reactions, okay? So if we're, one of the things we're concerned about these days is, and we should be, is how we make energy. Because every form of energy that we can make has its drawbacks. If we are making chemical energy. Okay, there's a lot of ways to make chemical energy, but the most common way of making chemical energy is using coal. And coal, for the most part, is carbon, and it's actually carbon and hydrogen. It's mostly hydrocarbons, all right? But we're using coal. Okay? Coal gives you a certain amount of energy per unit of fuel. But you know, to run a coal power plant, you got to have a lot of coal. You ever seen one of those coal trains? You know, where there's one, it's not even a boxcar, it's an open car on the top, one train car after another filled with coal, right? You got to have a lot of those to run a coal-fired power plant. And so they heat up the water, it turns a turbine, just like a nuclear power plant. Heats up the water, turns the turbine. And this spinning turbine is what creates electricity, okay? Well, that produces a certain amount of energy, okay? But the amount of energy we get from nuclear power is much greater for every unit, okay? But uranium is a lot harder to work with. First of all, it's radioactive itself. You got to look after the people that are digging it out of the ground because, you know, they're getting this increased amount of radiation, so they can only have so much. And then once you have to process this stuff, because you can't use just regular uranium out of the ground for the most part because it's just not radioactive enough. So you have to enrich the uranium. Okay? So instead of uranium coming out of the ground, which is almost all uranium-238, with a very tiny amount of 235, we've got to get rid of a lot of the 238 and leave behind a lot more of the 238, get rid of a lot of the 238 and leave behind all of the 235, and so it's called enriched uranium. When you hear that term on TV, it means that we've taken out a lot of those atoms or isotopes of uranium-238, so that we've got a higher percentage of 235. Think about it this way. If you had a glass of water with some salt in it, okay, and you leave it sitting on your kitchen counter for a few days, what's going to happen to it? Really? You don't know what's going to happen to a glass of water sitting on the kitchen counter? Evaporation. The water molecules are going to leave slowly, right? But the salt ions don't leave. So because the water molecules are leaving, but the salt ions are not leaving, we're increasing the concentration of the salt in what remains of that solution. Does that make sense? Okay? So this is the same kind of idea behind enriching uranium. Now you can't just leave it out on the countertop. It doesn't work that way. But we enrich the amount. We increase the percentage, the concentration of the form of uranium called 235, which is more radioactive. And you need to do that to make it work. So if we're going to use fission energy, we're going to use enriched uranium. Uranium, yep, okay. That makes sense? And we can't do power from fusion, but if we could, oh my, okay? Theoretically, it's possible. We know it's been done in sort of a laboratory setting. If you saw the laboratory, you'd say, wow, this is done in a laboratory. This is some kind of huge industrial process here. And it kind of is, okay? It takes a lot to make it happen. We just can't control it well enough to put it in a big power plant sort of setting. But for that, all we need are forms of hydrogen, okay? So we could use, what we need to do is to get, let's see, to be deuterium, probably, okay? That's what, because you can put two deuteriums together and make a helium, supposedly. We may also have to have tritium. I don't know if that has to happen or not, but that's why Dr. Octopus wanted tritium to do his fusion reaction. Yes. Okay. Y'all don't know who Dr. Octopus is? I'm talking about Dr. Octopus. Nobody knows. You know. Good for you. All right. So see, reading comic books actually has some value here.
Can I just watch the movie?
Sure, but not in here. You don't expect that.
Not.
No, of course not. That's right. Okay.
Movie date.
Movie date. There you go. All right. You know what? We've got a chemistry club. The chemistry club could have a movie date. Okay, we can get.
They don't want me. Chemistry class.
They don't want you?
No.
What now?
Chemistry class for a movie date. have a movie in here.
I just said we're not going to do it in here. We don't have time to do it in class. Okay.
So much beauty.
Now, if the whole class wants to, like meet at somebody's house, get the movie, that's fine. Okay. We can do that. Anyway. And so the amount of energy you get from a sample of coal is way small. The amount of energy you get from uranium using fission power by comparison to the amount, so if you're comparing the same amount of coal and uranium and deuterium, the amount of energy you get out of this is just hundreds and hundreds and hundreds of times bigger each time, in each stage. Okay? And that's called an order of magnitude. All right? So every time, let's say you've got a 10 to the first power. Okay? Well, 10 to the first power is just 10, right? 10 to the 0 power is just 1, right? This is an order of magnitude larger than that. So you can tell about orders of magnitude by the exponents. Got it? And so 10 to the second, which is 100, is 2 orders of magnitude larger than this, and 1 order of magnitude larger than that, right? That makes sense? Well, that's a lot, okay? Okay, this is 10 times larger than that. And then 10 to the third, that's 1,000. That's 1, 2, 3 orders of magnitude larger than this one, okay? We're talking about, we're talking about like 5 orders of magnitude between coal and uranium. Difference in the amount of energy you can get out of the same amount of fuel, okay? And about, I forget, 3 to 5 orders of magnitude more energy out of the same mass of fuel for fusion, okay? I will look up the actual numbers and get those to you, okay? You don't have to memorize the numbers. The main thing I want you to know is many orders of magnitude larger than this, many orders of magnitude larger than that for the amount of energy you get out of the same mass of fuel. That's the main thing I want you to know. Okay? So, why do we want to do fission power? Because it's more efficient. Problem is it's got more problems, so we have to treat it with a lot of care. So a lot of regulation from the federal government and the state governments and things like that when you do fission power, when you build a nuclear power plant. Because right now, we can't do anything with the nuclear waste. Once you've depleted the amount of 235 and you don't have usable uranium that's enriched anymore, enriched enough to run the power plant, then we really don't have a reasonable way to deal with the waste. Have I told you all that already? Okay. So right now it's being stored right here in our fair state. Okay, just above the ground somewhere. All right. So not a good thing, but that's what we do with it. Great big giant size metal containers, filled with other stuff, and a little tiny sample of the uranium in the middle. All right. Anyway, so that's the basic story on nuclear power. Now, there's one other type of nuclear decay you need to know about. Well, actually, there's something else you need to know about. Let's look at your test reference here for a second, and let's find. I'll find it in a minute. I'll show you. Here you go. This is a graph that shows the nuclear decay series for uranium. And this is using uranium-238. Okay? And this is showing you some of what we just talked about. Okay? We said that uranium goes through alpha decay. And when uranium goes through alpha decay, the resulting particle has a mass 4 smaller. A mass 4 smaller, and that's 234. Well, that must mean we're making thorium here. Does that make sense? Okay? Thorium goes through 2 stages of beta decay. Okay? Thorium gives away a beta particle, creating an extra proton. Well, then we've got palladium. All right? And then that gives away a beta particle, creating another proton, which gives us another form of uranium, uranium-234. Uranium-234 goes through alpha decay, and we get this element with a mass of 230, and we got another form of thorium here. And that goes through alpha decay, so that form of thorium goes through alpha decay and becomes radium, which goes through alpha decay, becomes radon. Radon is particularly dangerous in our part of the country because radon is a gas, and it percolates up through the soil. Okay, we can also call that evolving through the soil, and gets trapped in your basement area or your crawl space under your house in some places, in some houses. Okay? Well, that's not good because it causes cancer. So you breathe that stuff in, you have a higher chance of having lung cancer. All right? Not good. So if you live in an area where there's a certain amount of uranium up under the soil so far down you don't even know it's there, but this radon is percolating up through there, you kind of need to know that. You know what I'm saying? I think the health department State Department of Health pretty much does a pretty good job of that, but maybe not enough for you. You got to decide what you're going to do. But anyway, that's the problem with radon. Then radon goes through a form of decay called alpha. It gives us polonium. All right, polonium is named for, nobody knows really? Poland, very good. You know why it's named for Poland?
Because Poland discovered it.
No, but somebody from Poland discovered it. Who was from Poland that was such a famous scientist that dealt with radioactive stuff?
Einstein.
Not Einstein. Who? There you go. The Curies. Okay? And so curium and polonium are both named for them, okay? And then you've got lead. Well, this particular form of lead is not very stable. Okay, this is lead 214. So it goes through alpha decay. That particle goes through two forms of beta decay. That goes through alpha decay, two forms of beta decay, and finally we get to a stable form of lead. And guess what we line things with to keep us from being exposed to too much gamma radiation? Lead. Okay? So, you know when you go to the dentist and they put that big old heavy blanket on your chest when they take an x-ray? Okay? Lead. Well, probably. I don't know. And, of course, the technician always walks around the corner before they stamp the x-ray picture because the concrete's pretty good about blocking x-rays as well. And since they're working with them all the time, they really need to be protected from it, more than us, most of us anyway. Okay? And that's why they have the little sign up there. If you're pregnant, make sure you tell them, all that kind of stuff. Got that? All right. So it's all forms of radiation. X-rays are a type of radiation that's also kind of dangerous to you. All right. So you need to know that uranium goes through series of decays. You don't have to memorize this decay series, okay? But I could give you the information to let you figure it out. You could write look at all these equations you could write. All of equations you could write, right? Until you finally get to lead. All right. I want you to know that uranium goes through these decay series. One of the stages you get to is radon, which is dangerous, and why. Okay. And then you finally get to a stable form of lead. Kind of in general, that's what I want you to know. Got it? Got that? All right. All right. Now, then I'll go into carbon-14. Now, so carbon-14, there are three relatively common isotopes of carbon. Carbon-12, 13, and 14. Okay, three relatively common isotopes of carbon, 12, 13, and 14. So carbon-12 has 6 protons, 6 neutrons. Carbon-13 has 6 protons, 7 neutrons. Carbon-14 has 6 protons and 8 neutrons. Okay? The reason I kind of pause and let you guys fill in the blank, and some of you are doing this and some of you aren't, because I'm trying to encourage you guys to think ahead with me, because that's active learning, right? I've talked about that a bunch already, right? The more you're doing that, and even if you're not speaking it out, you're doing it in your head. If you just wait for me to give you the answer, that's passive learning. Passive learning is not very effective. So you need to, even if you aren't speaking out, and I hope everybody starts to speak out, but if you aren't speaking out, at least let it go, work that out in your head. Try to think it through, because that active learning is a better way to learn. You're going to remember more of it without having to study so hard before tests. Okay? And still make a good grade. So carbon 12 and 13 are pretty stable. Okay? They don't decay. But carbon 14, on the other hand, decays. Now, carbon 14 is actually created through natural processes in our atmosphere. And so we are all breathing in carbon dioxide that has carbon 14 in it, a small percentage. And we know how much there is. We have a good idea that as scientists, people that are smarter than me, have a good idea how much carbon 14 there is in the atmosphere. And of course, as we increase the CO2 in the atmosphere, we have more carbon 14. So you kind of have to know that, how much carbon 14 was in the atmosphere to be able to use this stuff. And we know how fast it decays. So we take carbon 14 and we look at the percentage of carbon 14 and what it decays into. Okay? So carbon 14 decays, it goes through beta decay. Write an equation for beta decay of carbon 14, and let's see what it decays into. Okay, good. So carbon-14 goes through beta decay and decays into nitrogen-14, okay? Because it's going to create an extra proton. That's pretty simple, right? Pretty simple math there. Now we need to talk about half-lives, and all these isotopes that are radioactive have half-lives. But this half-life of carbon-14 is the only one that I expect you to know from memory, okay? The average half-life, or the half-life of carbon-14, is 5,730 years. So, if everything that's living and breathing, and that's all plants and animals, okay? Everything that's living and breathing, and that's all plants and animals, are ingesting or breathing in or using carbon-14 in some form, okay? Then there's a certain amount of carbon-14 in living creatures, right? It's plants and animals. Once we die, we stop breathing, right? So the amount of carbon-14 coming in stops. And so we can measure the amount of carbon-14 left in the percentage of carbons in the body. We know what the percentage of carbon-14 is in the atmosphere. We then know what percentage of carbon-14 you should have in your body. Once you die, then we should be able to look and see how much carbon-14 is left compared to all the other carbon and figure out how long you've been dead. And that's what they call carbon dating. And they've measured this back using living things that are still living, okay? Well, for example, you take trees, okay? You got a tree, and you can go back through. I mean, we got some trees that are very, very, hundreds and hundreds of years old, okay? You can look at all the tree rings, and so the carbon-14 builds up in those rings because it adds those new rings every year. And we can find out how much carbon-14 there was in the atmosphere by looking at those tree rings and sampling those tree rings, okay? And then you take a tree that's been dead and buried and compare those tree rings by the weather conditions. You can tell how those tree rings match up. We've gone back about 20,000 years, I think it is, using these processes to figure out with what should be reasonably good accuracy how much carbon-14 there was in the atmosphere, going back for quite a while. You can also use ice cores, because you go to Antarctica and you can look at the layers of ice, okay? And there's carbon, CO2, in that ice in there, and so you can figure out how much carbon-14, and you compare all this stuff together. So we can go back with a pretty good accuracy, we think, to about 20,000 years. Past that, it becomes a little fuzzier, but it's still, you can have a pretty good idea how long something's been dead. That makes sense? So if you want to know how long it was that some kind of creature lived, and you still have the organic samples, the parts of the body that are still there, then you can use carbon dating to figure out when it lived, or at least when it died, okay, which pretty much tells us how long ago it lived. That makes sense? Now, anything past that, we have to use other methods for dating things, okay? But if you're an anthropologist who's dealing with, pretty much plants and animals that are, haven't been dead like thousands of years, or billions of years or whatever, then this is a really important process, okay? And so when you hear or see stories about the Shroud of Turin and how they try to figure out how long that's been around, things like that, well, that's how they're using carbon dating, okay? The problem is that you get this contamination in the samples, because it hasn't been just treated with great care about any kind of other stuff getting in there. Dust, pollen particles, things like that get in there, and that all affects things. So you can't always tell for sure. But if you have a sample that's been, pretty much taken out of the atmosphere and it's been dead for a while, you can figure out how long it's been dead. That makes sense? But you got to look out for all those other things that come into it. Yeah?
What did you say the half-life of carbon-14?
5,730 years. So let's talk about what half-lives mean. A half-life, anybody who has not taken the Unit 1 test? You haven't taken the Unit 1 test? Uh-oh. Huh?
I'm taking it this afternoon.
You take it this afternoon? I might need to take you out. Yeah. No, because you need to know this too. You're just not going to be able to do the extra credit question. Okay? The extra credit question deals with half-lives. All right? Half-lives is the period of time it takes for half of a sample to decay. Okay? the period of time it takes for half of a sample to decay. Now, here's the strange thing. It might seem kind of strange if you've never dealt with it before about that. Every half-life is a little bit different. Okay, the 5,730 years half-life is the same, okay, but the amount might seem a little strange to you. Let's say we're going to start out with a sample that's 200 grams of carbon-14, okay? And so we're going to call this time 0 at the beginning of our counting, okay? And so the amount of years that have passed is 0. That's what I mean by time 0. Does that make sense? All right. So in 5,730 years, that'd be time 1. So that's our time period for half-life. That makes sense? Half of this is going to have decayed. Half of our amount of carbon-14 is going to have decayed into nitrogen-14. And so we're going to have 100 grams left. Okay? That makes sense? Yep. All right. Now, this is the part that tricks people up. The next half-life, which is double this, 5,730 years. So 5,730 years times 2, 11,460. Okay, and that's time. That's our second half-life. Well, now it's half of this first half-life. Whatever from here is half. Well, that's 50. Okay? And so our next half-life, that's 17,190 years. Half of this is going to be left. Does that make sense? And so that just keeps going on. Now, how long does it take to have no carbon-14 left?
Never. I mean, 'cause it just
That's it.
get bigger.
The answer is never. You're never going to reach the point where there's none of it left. Now, can we reach such a small amount that there's only one atom left and the half-life is gone? Yeah, sure. I mean, theoretically, I suppose. You know, that it kind of breaks down when you get down to individual amounts. We're talking about thousands and thousands and thousands and thousands and thousands of atoms of carbon-14 in your body. Okay? Because there's lots and lots of carbon. Let's say we have 12 grams is not much. Okay? 12 grams is a small amount of carbon. All right? In that 12 grams, let's see, how many atoms are there in 12 grams? 6.02 times 10 to the 23rd. Now that means it's 602 and 21 zeros. That's how many atoms there are in a 12 gram sample of carbon. That's a lot of atoms, right? Okay, that number is important, by the way. Okay, that's called Avogadro's number. Avogadro, A-V-O-G-A-D-R-O. It kind of sounds like avocado, but it's Avogadro. A-V-O-G-A-D-R-O, Avogadro's number. Now, Avogadro didn't figure out the number, but he came up with the theory that allowed scientists later on to figure it out. And that number is also important because it also gives us our concept of something called the mole. And the mole is not that little skin thing on your, the little dark thing on your skin, and it's not the little animal that crawls on the ground. The mole is the International System of Units designation for the amount of substance. And it's really, really important to chemistry. Okay, the mole is our unit of measurement for the amount of substance. All right, spelled M-O-L-E, but we shorthand it by leaving the E off. In German, they spell M-O-L. In Latin, it's M-O-L. And since the Germans, I think, came up with that word, mole, Shorthand MOL makes a lot of sense if I remember the history of it correctly. All right. So a lot of times we'll write it MOLE, and sometimes we'll write it MOL. It means the same thing. Okay. You don't really have a shorter shorthand for the element. The unit of measurement for mole. And it's almost a misnomer to call it a unit of measurement. It is, but it's also a counting number. Okay. So you have to kind of know the concept and what it means. All right. So Avogadro's number is the number of particles in a mole. Avogadro's number is the number of particles in a mole. And so in every mole, and not the animal the mole or the one on your face, but the measurement unit mole, in every mole of a substance, you have 6.022 times 10 to the 23rd particles. Okay, so in a mole of carbon, 6.022 times 10 to the 23rd atoms. Okay, in a mole of CO2, 6.022 times 10 to the 23rd molecules of CO2. In a mole of water, 6.022 times 10 to the 23rd molecules of water. In a mole of electrons, 6.022 times 10 to the 23rd electrons. That makes sense? Okay, particles. Got it? All right, in our sample of salt, in a mole of salt, there's 6.022 times 10 to the 23rd formula units. Okay? All right. So finish your worksheet tonight. Remember to come to class dressed for lab tomorrow. Got it? All right. Y'all stay warm.